probabilities apply to logical statements called events. So it is important to understand how logical statements can be built up from smaller pieces. As always, let's begin with a story.
The ranger studying the horde of monsters believes that it either contains a hippogriff or a bugbear or both. What is the negation of that statement? When calculating probabilities, it is often useful to be able to tie together or break apart logical statements into their pieces. In order to accomplish this, it is necessary to understand the main ways in which logical statements can be connected. The logical OR operator is applied to a pair of logical statements and returns true when either one or both of the statements are true. The logical OR of P and Q is written P or Q, where the OR symbol looks like an inverted mountain. For instance, a true or true statement is true, a true or false statement is true, a false or true statement is true, and a false or a false statement is false. This is equivalent to saying that the logical OR is true when at least one of the statements is true, which gives the following definition in terms of indicator functions. The logical OR between S1 and S2 is just the event that the indicator of S1 plus the indicator of S2 is greater than or equal to 1. Since logical OR was defined using addition, which is commutative, so is logical OR. For logical statements S sub 1 and S sub 2, S sub 1 or S sub 2 equals S sub 2 or S sub 1. This definition can be extended nicely to any finite number of statements, S sub 1 up through S sub n, or even to a countable sequence of statements. The countable logical OR of the sequence S sub 1, S sub 2, etc. is just the event that the sum of the indicators of those events is greater than 0. The logical AND of two statements, S sub 1 and S sub 2, written S sub 1 and S sub 2, where AND is the mountain symbol, is true if and only if both of the statements are true. So a true and a true is a true statement. A true and a false statement is false. A false and a true is false. And a false and a false statement is false. Now, logical OR kind of corresponds to addition, since the logical OR of S sub I is the sum of the indicators greater than 0. Logical AND is more like multiplication, since the logical AND of a set of values is that the product of the indicators of those values is greater than 0. So if I am interested in the countable logical AND of a sequence S sub 1, S sub 2, etc., that's just the infinite product as I goes from 1 to infinity of the indicator of the S sub i's greater than 0. Now the third major logical operator is logical NOT, which is also called negation. What logical NOT does is it changes a true to a false and a false to a true. So the negation of true is false, the negation of false is true. It can also be defined, as with the other operators we've talked about, using indicator functions. The logical NOT, aka negation of S, is the event that the indicator of S equals 0. Negation can also be used to define the complement of a set, the set of elements not in the original set. The complement of a set A, written A complement with a little superscript C, is defined as an object X is an element of A complement is the same as the negation that X is an element of A. So the complement of the set A consists of all elements not in the set A. When adding and multiplying numbers, there is an order of operations. Multiplication is done before addition. For instance, 3 plus 4 times 6 equals 3 plus 24 equals 27, because the multiplication is done before the addition in the statement. In the same way, there is an order of operation of logical operators. First comes logical NOT, then logical AND, and finally logical OR. That is, not comes before and, comes before or. So if I wanted to find the negation of 10 equals 11, or 5 greater than 6, and 3 less than 4, I would first do the not. 10 equals 11 is false, so not false becomes true. Then I would do the and. 5 greater than 6 is false, 3 less than 4 is true, so that becomes false. And then finally I would do the or. True or false equals true. Now fortunately there are 3 facts about indicator functions that enable us to turn problems involving logic into multiplication and addition. For any logical statements S and R, the following 3 statements hold. First, the indicator of the negation of S is 1 minus the indicator of S. The indicator of S or R is the indicator of S plus the indicator of R minus the indicator of S times the indicator of R. Finally, the indicator of S and R is just the indicator of S times the indicator of R. These 3 facts about indicators allow us to break apart any logical statement involving a finite number of not, and or into additive and multiplicative statements about the indicator function of the individual events. Now, one thing to notice is that the indicator function is a one-to-one function, which immediately tells us that for any logical statements P and Q, P is going to equal Q if and only if the indicator of P equals the indicator of Q. This allows us to work out more complicated equations using arithmetic instead of logic. So for instance, for a logical statement S, the negation of S equals S itself. And this is true because the indicator of the negation of S is just going to be 1 minus the indicator of the negation of S. And then the indicator of the negation of S is 1 minus the indicator of S. So 1 minus the quantity, 1 minus indicator of S, is just the indicator of S. And since the 2 statements have the same indicator function, they have the same truth value. Indicators over logical AND become multiplication. So if I want the indicator of the logical AND of a sequence of events S sub 1, S sub 2, and so on, that's just going to be the product of the indicator of S1 times the indicator of S2, and so on. Now at this point, something more advanced can be proved, namely De Morgan's laws. These allow logical NOT to be distributed over logical OR and logical AND. First, consider distribution over logical OR. For any 2 events S and R, the negation of the quantity S or R becomes the negation of S and the negation of R. So when you distribute negation over OR, it changes the OR into an AND. Similarly, if you distribute a negation over an AND, it turns the ANDs into ORs. So now let's talk about the story that we had at the beginning of this lesson. In the ranger story at the beginning, let's let S1 be that the hoard contains a hippogriff, and S2 is that the hoard contains a bugbear. Using our logical notation, the ranger believes that S sub 1 or S sub 1 is true. So the question to be considered is, what is the negation of this event? Using De Morgan's laws, the negation of the quantity S1 or S2 is the negation of S1 and the negation of S2. So in English, the negative of the statement, the hoard contains either a hippogriff or a bugbear or both, is the hoard does not contain a hippogriff and it does not contain a bugbear. Finally, say that S sub 1 implies S sub 2. If whenever S sub 1 is true, then S sub 2 must be true as well. For instance, if x is greater than 3, that implies that x is greater than 0. Since whenever x is greater than 3 is true, it must also be true that x is greater than 0. Note that the reverse implication does not hold. Just because x is greater than 0, there is no guarantee that x greater than 3 will be true. In the end, this means that either not p is true or both p and q are true. We can write that as either not p or q is true. So that's our definition. We're going to say that S sub 1 implies S sub 2 to mean either not S1 is true, that is S1 is false, or S2 is true. Now, logical implication is closely tied to the notion of one set being a subset of another set. For two sets A and B, we say that A is a subset of B and write A subset symbol B to mean that whenever X is an element of A, that implies that X is also an element of B.
So now we know how to put logical statements together using logical operators in order to build more complicated statements. See you next time.